Is it? Yes, so it is recording, and let me start by sharing my screen. Yeah, let's see. So where is it? Here. So this is, I scale my entire screen, share. Yeah. All right. Okay, so is it working? Do you see lecture 3 scribbled SI425?
Yes, ma'am.
Yeah, okay, excellent. All right.
Yes, ma'am.
All right. So let's see, where were we last time? Yeah, so we sort of saw a little bit of, introductory logic and how are proofs in mathematics written. So we actually didn't see proofs, but sort of tools to write proofs. And we try to define real numbers. Yeah, we have still not defined them. So to define real numbers, one begins with the set of rational numbers and tries to construct a set that satisfies the properties that we postulated for the set of real numbers. What are those properties? We said that we assume that there is a set R whose elements are called real numbers. Yeah, so let me sort of go back to those notes. Um, there is a set R. Yeah. Can you please mute your mic? Yeah. Uh, so there is a set R whose elements are called real numbers, which contains the set Q of rational numbers, in particular the additive identity and the multiplicative identity, which we denote by 0 and 1 respectively, such that the following three types of properties are satisfied: the algebraic properties, the order property, and the completeness property. Yeah? And why is there a need to define such a set? We saw in example last time that there is indeed a number which cannot be represented as quotient of two integers, yeah, which means that it is not a rational number. So suddenly the complement of the rational numbers is non-empty. Yeah. Okay, so we started by listing the algebraic properties. There are two set of binary operations, multiplication and addition respectively, and they satisfy these properties. I will not run through again, we have seen that. Yeah, so what I'll rather focus is, let's start with the order properties, yeah, and continue from this point. So we said that we assume that there is a non-empty subset of the set of real numbers, which I'm going to denote by R plus, and we are going to call this as set of positive real numbers satisfying the following two properties. The first one, which I have written as O1, says that, so is this size okay, or I can sort of zoom out a little bit? Is that better? Yeah. Okay. Yeah. That given any real number, one and exactly one of the following statement is true. Either that real number A belongs to this non-empty subset, or that real number A is the additive identity, which I have denoted by 0, or the additive inverse of that real number belongs to that non-empty subset. And the property O2 says that if there are two members, two elements A and B in this non-empty subset, then when we apply these binary operations, namely plus and dot, which is addition and multiplication, then the output, the sum, and the output also continues to be in the same non-empty subset. Okay. So we are going to say that we are going to assume the existence of this non-empty subset. We say that there is a non-empty subset of this. Yeah. Is this okay with everybody present here?
Yes, ma'am.
Yes. Okay. So we'll move on from this. Yeah. So given the existence of this set, let's see. So given the existence of this non-empty subset, given the existence, what am I going to do next? of this non-empty subset of R satisfying O1 and O2, I am going to define an order relation on the set of real numbers. Yeah. So one can define an order relation. What is that I mean by this? Sorry, by mistake, an order relation on the set R of real numbers in the following manner. Yeah. Okay. Let's see. I'm going to say for any two elements in the set R of real numbers, I'm going to say, so this is my definition, define A to be less than B B, and I'm going to write it as, I'm going to use this symbol, if the following is true. Yeah, if, so I take B and sum it with the additive inverse of A, and if that sum happens to lie in this non-empty subset of R, whose existence we postulated just above, then we say that A is less than B. Yeah, is this okay? Does everybody follow this definition? See, this is a notation that I'm introducing. When I say A is, I'm going to define this, A is less than B, and I'm going to write it as like this. If I consider B plus, apply the binary operation of addition, plus the additive inverse of A, this output, whatever I get, this lies in this non-empty subset of R. Is this okay? Is that a yes with everybody present here?
Yes, ma'am.
Yeah. So you may wonder, what am I doing? Where are we heading? Yeah, go ahead, go ahead. Somebody has a question. Yeah.
Ma'am, shouldn't the statement be that, shouldn't it be a double implied statement? Not just a single
Yeah. So this is a definition. You know, this is an if and only. This is a definition. If this happens, then we say A is less than B. If A is less than B, then this happens. This is a definition. Yeah, there's no implication here. Is that okay?
Yes, ma'am.
Yeah. Yeah. All right. So shall I assume this definition makes sense to everybody present here?
Yes, ma'am.
Yes. Yeah. Yeah. We will see where are we heading. Yeah. As I said, you know, bear with me for some more time. Yeah. Okay. So what am I going to do with this notation? I claim that with this notation, one can sort of deduce something more. I can write something more. So I say that, so let me make this following point. Let me write that down and then I'll try to explain it. So with this notation, so which notation I'm referring to? A is less than B. I say that it follows from the algebraic properties of R. What follows? That I can say something, I can describe this non-empty subset of R. I can say that this is all those elements in R. So what am I going to say? Yeah, so let me try to scribble in a different color so that, yeah. So I want to describe elements of this non-empty subset. I want to describe this set. Yeah. So I have this information with me. So what am I going to say? I'm going to say the following. Yeah. So let's look at elements of this non-empty subset. Yeah. So I'm going to write this as, use the fact that there is an existence of additive identity guaranteed. Yeah. So I'm going to write it as X minus the additive identity. Yeah. Is that okay? Yeah, so this is x plus the additive inverse of the additive identity, which is 0. Is this okay? So any element in this non-empty subset, I can write it like this. Yes. Now, what is the meaning of this statement? That this is indeed in this. If you go back to this notation, that this just means that this additive identity is less than x. This exactly means this. Is that okay in view of this definition? Is that okay? Yeah.
Yes,
So
ma'am.
coming back to
Yes,
this,
ma'am.
this is exactly saying that this set which I have described above is nothing but all those real numbers which satisfy this condition. Yes. This is exactly what we know all along from our previous knowledge, right? So what O1 and O2 above tell me in view of, in this notation is that this non-empty set is exactly this. Yes? Yeah? All those real numbers which satisfy the following order relation, that x is 0, the additive identity is less than x. Is that a yes with everybody present here?
Yes, ma'am.
Yes.
Yes, ma'am.
So I am going to say that with this relation that I have defined here, that means this symbol that I have defined here, the set R is an ordered set. Yeah. So let me write down what is an ordered set, and then we will see. This is another definition. So this is another definition. An ordered set yeah, so it means a set with a symbol like this. Yeah, a set with a relation. An ordered set, so there are two things to this. You have a set and a relation. Is a set with a relation satisfying the following two properties. What are those two properties? First one, so if I have two elements in this set, then I say that exactly one of the following statement is true. One and only one of the following statement is true at any given point of time. Yeah, so what are those? So let me sort of scribble on the next page. What are those? So either, so I have already, I'm given this set and I already have a relation on this set. Yeah, so given two elements of this set, I'm going to say that either x is less than y, this less than is defined in terms of this relation, or the two are equal, or the other possibility is, so well, I should not write it as or, because there are three things here. Yeah. Yeah. So one possibility is this, the other possibility is this, or yeah. So is this okay? The first thing makes sense to everybody. So I have a relation and given two elements, one and only one of the following is true. Either x is less than y as defined by this relation. So this less than is going to be how this relation defines this it to be, right? Or the two are equal or y is less than x. So this is the first one, and the second one required is that given three elements, in this set, if x is less than y with respect to this order relation and y is less than z, then it would follow that x is less than z. Yeah. So when I have a set S with a relation satisfying 1 and 2, we say that this is an ordered set. Yeah, perhaps you've seen this before. So what I want to say in this context of, in the context of what we are discussing is that properties O1 and O2 tell me that I can define an order relation on R. I can define this symbol, right? And once I've defined this symbol, properties O1 and O2 tell me, what do they tell me? That the set of real numbers with this relation that I have defined here, this is an ordered set, meaning it satisfies 1 and 2 that I have listed here, these two properties. Is that okay? So let me write that down. The upshot of all of this discussion is that R with this notation is an ordered set. Is this okay? Is that all right with everybody present here?
Yes, ma'am.
Yes, ma'am.
Yeah, please bear with me. As I said, this may look very weird, but yeah, so have some more patience is what all I can say. Yeah. So before going ahead, so what have we stated so far? We have stated the algebraic properties of R and we have stated the order properties of R. I want to make one more statement before we move on to the next set of properties. Yeah. Okay. So what is it? Please note, at this point of time, what do I want you to note? Yeah. So if you go back to the set Q of rational numbers, please know that this. So we noted, after the algebraic properties of R, please know that if you consider the set Q of rational numbers with the binary operation addition and multiplication as we defined above and restricted to the set of rational numbers, then the set Q of rational numbers also satisfies. So let me write that down. Yeah, sorry. So two things to be noted here, that if you consider the set of rational numbers and apply these binary operations, then they also satisfy, all those algebraic properties that we listed for the set R. They satisfy, A1 up to A5, M1 up to M4, and the distributive property. Yeah? So this so that means that this is indeed a field. And another important thing to note at this point is that this is an ordered set. Yeah, the set of rational number is an ordered set. Yeah. So when I say that this is an ordered set, as I said here, when you say that it is an ordered set, you have to define a set and you have to also give me a relation on that set. So what is the relation here? So this is an ordered set with the following relation. So I have to define the meaning of this symbol. So if R and S are any two rational numbers, what is the meaning of this symbol? Yeah. So I say that this is defined to mean that S minus R is a positive rational number. Yeah, is this okay? Is this okay with everybody?
Yes, ma'am.
Yes, ma'am.
Yes. All right. Let me see how many of you are there today. 54 of you. Okay. All right. Okay, let's see. All right. So let's go back to in here. Right. Let's go back to this slide. Yeah. All right. We just noted that the set Q of rational numbers has the algebraic properties and the order properties described here. Right? Is that okay? Yeah. 1 and 2 are also satisfied by the set Q of rational number. Right? But we have seen an example of a number, namely square root of 2, which cannot be represented as a rational number. Yeah? Is that okay? Does that make sense to everybody?
Yes, ma'am.
Yes. So this observation shows that there must be an additional property that characterizes the set R of real numbers. There must be a property that the set R has, but the set Q of rational numbers do not have, right? And that's exactly the completeness property, as we will see in a few minutes from now, right? So what am I going to do next? I'm going to talk about the completeness property of R next. Is that okay? Sounds like a plan?
Yes. Yes, ma'am.
Yes? Okay. All right. Let me go to the next page. This is page number 40. Okay. All right. So what am I going to do? We are going to state. So I'm going to write here towards the completeness property of R. Yes. All right. So why do I say towards the completeness property of R? Well, there is some groundwork needed before we can actually state this. Yes. Okay. All right. So we will need to sort of develop some language before we can state this. All right. Yeah. So let's start with this. So let S be a non-empty subset of R. Yeah. So let's define a couple of things. Let's see some examples and let's see. We say that we define S is said to be bounded above if I can find if there is an alpha. So if there exists a real number alpha such that what happens? X is less than equal to alpha for all elements of this set. Okay, all right. So couple of things here, right? So first thing is that I have not defined this notation as yet. Yeah, so let me clarify that. Yeah. So given two real numbers, the notation A less than equal to B, yeah, with the understanding A and B are two real numbers, means that either A is less than B or A is equals to B. Yeah, you know, so this is in terms of the order relation that we defined in the previous slide. Is that okay? Yeah. So once we have understood this notation, I believe this makes sense. Yeah. When do we say a non-empty subset of R is bounded above? Provided I can find one element alpha in some element in in the real numbers such that X is less than equal to alpha, and this is true for every element of X. Is that okay?
Yes, ma'am.
Yes. Is that okay? Yeah. So let me make this point. Any such alpha is called an upper bound of S. Any such alpha is called an upper bound of S. So, this definition does not say that S is always bounded above, that I can always find an alpha. Whenever I can find an alpha satisfying this condition, then we say that the set S is bounded above. And any such alpha is called an upper bound of S. And please note that there is no uniqueness here as far as alpha is concerned. If a set S is bounded above, which means that I can find one such alpha satisfying this condition here, then please note that alpha plus 1, alpha plus 2, alpha plus 3, they're all upper bounds of S. Yes. So if a set S has one upper bound, then it has infinitely many upper bounds. Is that okay? Is that okay? Yeah. So for those of you who are seeing this for the first time, let me just write this down. If a set S has one upper bound, then S has in fact infinitely many upper bounds. Right? So there is no uniqueness statement here. All right. Everybody with me so far? Yes, is that okay? Yeah. All right. Okay. Let's see. Okay. All right. Let's see the next definition. So likewise, when do we define a set to be bounded below? Yeah, so let me just write it for the benefit of those who are seeing this for the first time. A set, so S is again, a non-empty subset of R. We say that S is bounded below if I can find, if there exists a beta. Yeah, so let me write this a bit carefully. If there exists a beta, if there exists an element beta such that the following is true, such that the following holds true. Beta is less than equal to X, and this is true for every element in the set X. Yeah. And whenever such a beta exists, we call that beta is a lower bound for X. Any such beta is called a lower bound for X. Yeah. So just like before, if a set S has one lower bound, then it has infinitely many lower bounds. If beta is a lower bound, then anything less than beta is also a lower bound. Is that okay? Yeah, we will see some examples, but let's develop some theory, some definitions, so that we can see some interesting examples. Is this okay?
Yes, ma'am.
Yes. Please, if something is not clear, there is some sticky point, please sort of feel free to stop me, unmute yourself and ask. Yeah. Okay. Any questions up till this point? Any questions? Okay. All right. So I assume no further questions. So let's see. Let's go on to the next definition. S is said to be a, so given S, I am working under the same assumption. S is a non-empty subset of R, and we say that S is bounded. When do we say a non-empty subset of R is bounded? We say that S is bounded provided S is bounded above as well as bounded below. Yeah, in the sense that I have defined above. If it is bounded above as well as below. Yeah. So this is when we say if S is bounded. Yeah. And if this does not happen, otherwise S is said to be unbounded. Sorry. Yeah. Which means that it may happen that S is bounded below but not bounded above. Yeah. In that scenario also, we will say that S is unbounded and vice versa. Is that okay? Everybody with me?
Yes, ma'am.
Please ask if there are any doubts, questions. Yeah. All right. Let's take an example. Yeah. It has been a while that we talked about examples. Let's see. Example. Let's consider the set n of natural numbers. Right. So what can you say? Is the set of natural numbers bounded below? Yeah. Question. Is the set n of natural numbers bounded below?
Yes, ma'am.
I repeat my question. Is the set n of natural numbers bounded below?
Yes, ma'am.
Yes, ma'am.
Yes.
Yes. So if you say it is bounded below, can you give me a lower bound for the set of natural numbers?
0. 1.
1. 1.
1.
1. 1 is a lower bound. Anything else?
1 and anything less than
Are there any other lower bounds you can think of?
0.
0.
any
Anything else?
negative
Sorry?
multiplier.
All the negative terms.
Yeah. So in fact, any real number which is less than or equal to 1 is a lower bound for this set, correct? Yeah. So yes, and any real number, yeah, beta less than equal to 1 is a lower bound for the set. Lower bound. What did I write? Yeah, is a lower bound for the set of natural numbers. Correct? Yes?
Yes, ma'am.
The next question is the set n of natural numbers bounded above?
No, ma'am.
No, ma'am.
Yeah.
No one.
So it seems like this is not bounded above, right? So can you provide me a rigorous argument why is that the case?
If we assume any upper bound, say,
Sorry, louder, louder.
if we assume any upper bound, say alpha,
Yes.
then, and let us assume alpha is an integer, just
Okay.
for each. So alpha plus, then every element of n should be less than or equal to alpha, but
Yes.
alpha plus 1 also belongs to n.
Yes, but this is under the assumption that the upper bound is an integer. What if alpha is not an integer? What if alpha is a rational number? Then alpha plus 1 may not be in this set, right?
Ma'am, we'll just take any epsilon greater than 0 that it makes n. Ma'am, we can
Yeah, so you have to
simply
sort of work it around. Yeah, so we will, so one goal of this course is to provide a rigorous answer to this question. Yeah, do we understand? There is a little gap in your argument.
Yes, ma'am. Yes, ma'am.
Yes. Okay. So let's, for now, I'll just leave it here, and maybe towards the end of today's class, I'll try to answer this question. Yeah. For the moment, let me move on to the next example. So everybody else, is this okay so far?
Yes, ma'am.
Yes.
Yes, ma'am.
All right. So let me see. Let me try to give you one more example to sort of illustrate what is happening here. Okay. So let's consider another set. Yeah. Let's consider. So my set is here. I am going to talk about all the rational numbers whose square is strictly less than 2. Yeah. This is my set. Yes. So clearly this is non-empty, right? In order to talk about bounded above and bounded below, I need to be sort of first ensure that the set is non-empty. So is the set S bounded above?
Yes, ma'am.
Is S bounded above?
Yes, ma'am.
Yes. So can you give me an upper bound for S? Can you give me an upper bound for S?
Root 2.
Something simpler. In fact, 2 is an upper bound for S, isn't it? Yes? Yes? Yes, you don't have to think so. Yes? Everybody with me? Yeah. Next question. Is this set S bounded below?
Yes, ma'am.
Is this set bounded below?
Yes, ma'am.
Yes. Can you give me an lower bound for S if you say it is bounded below?
-2.
Minus 2 is a lower bound, right? Very nice. All right. So these two examples, are they okay with everybody present here?
Yes, ma'am.
Is that a yes with everybody present here?
Yes.
Yes. So, let me try to scribble something. Yeah, let me try to draw a straight line. Not too bad. Yeah, so suppose I am going to jot down. So this is my real line. So suppose some points that I have jotted down. This is my set S. Yes. So if this is my set S, so in this picture here, S is bounded above as well as bounded below, right? So everything that appears here to the right of S, all of these are, so over here, all of these are, what are these in green? They are all upper bounds of S. Is that okay? Is that a yes?
Yes, ma'am.
Yes, ma'am.
Yes.
Yes,
And
ma'am.
everything to the left, all of that appears here, these are all lower bounds of S. Correct? And as we emphasized before, there is no uniqueness statement here, right? There is no unique upper bound. There are infinitely many upper bounds of S provided one exists. Yeah. And as before, if S is bounded below, then there are infinitely many lower bounds for S. Now, what am I going to do next? In the set of these upper bounds, sorry, I should not have done it, but anyways. So in the set of these upper bounds of S, I am going to single out the least element. Yes? Yeah? Makes sense to everybody? Yeah, I am going to isolate the least upper bound. So in the set of upper bounds of S, I'm going to talk about the least element. Yeah. So let me make that definition and maybe, yeah. So is this okay? Do you see where am I heading X? Does everybody see that? Yeah. So let me try to write
Yes,
that
ma'am.
down. Yeah. Okay. So this is the next thing. So as before, S is a non-empty subset of R. So let S be a non-empty subset of R, and suppose that S is bounded above. Yeah, we just talked about what it means to be bounded above. Suppose there exists an element in S satisfying the following property. Yeah, so let me make this statement. Yeah, suppose there exists an element uh, so S is a non-empty subset of R, which I am assuming to be bounded above, and suppose that there is an alpha satisfying the following. Yeah, what is that? One, alpha is an upper bound for S. Yeah, so what does it mean? Saying that alpha is an upper bound for S, we know what does it mean? It means that the following is true, and this is true for every element of S. Is that okay? And the second thing is that, yeah, so we talked about this, right? If alpha is an upper bound of S, there are many upper bounds for S. Yeah. The second thing I demand is that for any other upper bound, U of S, I demand that U satisfies this, right? So what is this? I am saying that given a non-empty subset which is bounded above, suppose that I can find a real number alpha such that one alpha is an upper bound, and if there is any other upper bound U for this set S, then alpha is less than or equal to U. Yeah. So what am I doing? If you go back to the picture here, I am trying to single out the least element in the set of upper bounds. Is that okay? Yes? 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 So if that happens, then I say that if there is an alpha satisfying 1 and 2, I say that then alpha is called the least upper bound for S. Yeah, so there's another name. This is called the least upper bound or the supremum for S. Yeah, and the notation is that alpha is equal to the supremum of S. Is that okay? Yeah. So let's just ponder on this statement for a moment. Yeah. I am not saying that the least upper bound always exists. If there is something which satisfies 1 and 2, then we say that that is the least upper bound. Is that okay? So I think, let me go back to where we are. All right. Okay. So in the afternoon, when we meet at 2, we are going to start with this definition and many more examples. But for now, I'll just pause for 2 minutes and ask, are there any questions so far?
No, ma'am.
Yeah, so this looks like there's too much going on, but don't worry, we will take up examples, non-examples, and we will see where are we heading. Yeah. Hopefully you will be better off in as I sort of try to run through this introductory part. Yeah, when you see some concrete examples, you will feel a lot better, hopefully. Yeah. So I think with that, I'll stop right here for now, and we continue in the afternoon at 2. Yeah, is that okay?
Okay, ma'am.
Yeah.
Okay, ma'am.
All right.
Yes, ma'am.
Yeah, thank you so much for your time. And let me stop sharing my screen. How do I do that? Stop sharing. Yes. Yeah. All right. Thank you so much for your time. We meet again at 2. And as I said before, please stop. If this looks like too much heavy material, stop me. If looks like too fast, stop me. If looks like too slow, give me feedback. Yeah. All right. Have a good day. Have a good rest of your day.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
You're welcome.
Thank you, ma'am.